Welcome, everybody. Today we are hosting Shuyang Ding from the Johns Hopkins University in Baltimore. Shuyang and I met, I think, for the first time in 2016 when I was visiting JHU, but we probably connected, I'd say, this year during the MT Marathon. And he already taught me and told me about his methods for interpretability in NLP via saliency gradients. And immediately after that, I was already able to use his ideas to visualize the gradient flow and information flow in my document-level machine translation systems. So where the stuff is looking at antecedents and translations. So that was very exciting. And today he's going to talk about his original idea and I think also about new research that I haven't heard about yet. So I'm looking forward to that a lot.
All right. Thanks for inviting me and thanks for the introduction. Okay, as promised, I'm going to tell you something today about using interpretability techniques invented in computer vision to improve interpretability for NLP models. The work presented here are done in collaboration with my advisor, Philip Kuhn, and my colleague, Hainan Xu. If there are any questions during the talk, feel free to interrupt me and ask questions. We have a 1 hour and 30 minutes stop, yes. Right? So this talk will probably go on for 15 minutes without questions, so should leave ample time for questions. All right, so here's an outline of the talk. I'm going to start by taking you through a quick tour of interpretability, get you up to speed about what's happening in this field of research, especially in computer vision. And then I'm going to talk about two pieces of work that I've done in this space. The first one is about uncovering word alignment from a neuron T system, and the second one is about benchmarking and evaluating interpretations using lexical agreement annotations that exist in NLP literature. And finally, I'm going to briefly talk about some future works that I want to do. All right, let's get started. So recently, whenever I go to a conference and I talk to people, they ask me, oh, what you do recently? I say, oh, I work on something related to interpretability. This is the face I usually get. So the big question people tend to ask nowadays, a lot of people care about interpretability, but we don't really know what is interpretability. So if you look at the existing literature in interpretability, unfortunately, there isn't a very monolithic concept or a very formal definition about what is interpretability. But today I'm going to give you some idea about what's going on in this research area by giving you some idea about what people actually mean when you talk interpretability, although it's not a monolithic concept. So the categorization of this, this meaning is proposed in this paper by Limpton 2018. I think it's called The Mythos of Interpretability. If you haven't read that paper, I definitely recommend you to do, even if you're just remotely interested in this topic. So the two categorizations I'm going to talk about, the first one is about building transparent models to do NLP tasks, and the second one is about doing this post-hoc interpretation. So to illustrate the difference between these two goals of interpretability, I'm going to introduce this toy example. So suppose you have a really fancy speaker that's connected to all of your gadgets. You have a TV, you have CD, laptop, whatever. And for some reason, the speaker is giving you this cracking and popping noise. And you're sure that the speaker is fine. So you try to figure out which input is the culprit. And when you open the cable box, whatever, that connects to your speaker, it looks like something like this. So just a little bit of interaction. What would you do in this scenario? Any ideas?
Unplug them one by one.
Right. That's a good one. What else?
Bluetooth.
Sorry?
Bluetooth. They're ruining you.
Bluetooth doesn't help.
All right, anyway, I'll give you some options. So the apparent and tedious thing they probably don't want to do is to rewire the cables. So what this is basically doing is that you're building a transparent model to do the same task. So in this case, because you have sorted out all the cables, it's pretty easy to figure out which are the input, like giving given you know like which input the speaker is playing, right? So this is talking about building transparent models, as I just said. So what this is doing is that you're basically building another model that achieves the same task but with like easily explainable behavior. In terms of migrating this concept into like NLP, most people will probably agree that the most popular deep learning NLP models are not the most explainable models. So what models are? Well, it's actually an open question, but just to give you some idea, one might think that log linear model is an interpretable model because if the feature has a very high weight, then probably that feature is important. And also some people will probably argue that attention is somewhat interpretable in that if the attention weights is looking at a source word, it's sort of mean that the source word has play a big role in the translation of this corresponding target word. We're going to talk about this briefly, like in 15 minutes more. All right, but for most people, we're just probably too lazy for that. We just want to keep the model intact and just but still get some kind of interpretation of the model behavior. So in that case, what you want to do is something called post-hoc interpretation. So one thing you can do is that you can ask a human, right? You can listen to the speaker and say, oh, this is a program from CNN, so it must come from the TV box. So basically what this is doing is that you're doing this interpretation with a standalone model, but this model is doing a different task in the sense that the original model is taking the electric signal as the input and transform that into the sound. Whereas a human, when they are doing this task, what they're doing is that they're taking the sound as the input and give you a distribution over which source is the culprit for this input, right? So it's a different model that's doing a different task. So another way you can do something is that you can either jiggle the cable to create some perturbation in the source, or as someone just mentioned, you can cut some of the cables to just black out some of the input. So what this is basically doing is that you're trying to come up with some interpretation by evaluating the sensitivity of the output with regard to each individual features. So throughout this talk, I'm going to put a lot of stress for this approach because this is apparently what people use in computer vision. Okay, so to talk about this approach, I'm going to do a little bit abstraction of the toy example. So suppose this cable you have can be abstracted into this black box model. And so what this is doing is that you have a four-way classifier that takes four individual input and outputs some kind of class labels, right? And the problem you're trying to solve is that given an output, you're trying to figure out which input is contributing most to this output, okay? And the jiggle the cable approach that I just talked about now is that you're basically adding some kind of perturbation to some feature in the input, and then correspondingly you will get some perturbation on the output. All right. So the problem is that if you intuitively, if you apply a big perturbation on the source, you will correspondingly get a big perturbation on the output, right? So what you really want is some kind of relative sensitivity that defines something like this. And if you still remember some calculus, when delta x approaches 0, this is really just a partial derivative of the output with regard to the input that you're trying to perturb. So from now, we're going to define this partial derivative as saliency, which is, you'll keep hearing this term like throughout this talk. All right, so what's good about this saliency definition? So the first one is that, remember, like when developed this saliency notion, I haven't made any kind of assumption about the architecture of the model. So you can really just apply this to any deep learning model that you're interested in. And the second thing is that if you have ever used any kind of deep learning toolkit, you should know that partial derivatives are really easy to obtain. You basically do the forward pass, and you just call backward function, right? So you don't really have to write a lot of code or actually do the perturbation for the forward step. So it's pretty easy to do. So apparently, because of this, it's really popular in vision. So for this example, this is trying to interpret the image classifier. So the input in this case is the image, apparently. And then on the output, you're trying to output some kind of distribution of the class labels about what is the most salient object in this image. And then for interpretation part, what you do is that you take some class label, and you get a corresponding score of that class label, right? And then you basically take gradient with regard to each input feature of that prediction score. And basically here, if you look at the saliency map, it's trying to tell you for each pixel what's the magnitude of the saliency here. So in this case, this image seems like a monument or obelisk. But when you look at the saliency, it's not all concentrated in that monument thing, because you still get some kind of saliency feature on the sky and on the cloud. So there is some noise associated with this kind of approach. So from this point until the end of this first section, I'm going to talk about two advanced way of computing saliency. They're still based on this notion of like using gradient to evaluate the sensitivity of the feature, but they have their own way of like solving whatever problem they come up with. Okay, so the first one I'm going to talk about is this thing called smooth grad. So the basic idea about smooth grad is that they think, well, the gradient is actually a very local measure of sensitivity in the sense that if you have a highly nonlinear model, like a lot of the deep learning model that you build, you may have a lot of these pathological points where the gradients are not really a good representation of the granularity of the sensitivity that you care about. And you may get a lot of noise with these gradients. So here's a toy example. Suppose you have this output y that you care about, and by changing some feature value, x, the output y would appear change like a curve like this. So basically, most people will probably agree that when you increase x, it will positively contribute to the activation level of y. But if you happen to evaluate the gradients at this point, then what you get is a large negative gradient, which in this situation, it means that x is negatively correlated with the prediction score y. So in that sense, you'll probably consider it as sort of a noise. So the solution proposed by this smooth grad method is that you calculate saliency not for just the original, like a certain example input. What you do is that you construct multiple copies of the same input, but you construct these inputs by corrupting the original example using a Gaussian noise, right? And then what you do is that having gotten these different versions of saliency, you average them, hoping that it cancels out the noise, and also you get a large scope, a slightly larger scope of the saliency of the feature beyond the very point of the example input, right? So basically, in this case, what you do is that instead of just evaluating gradients at x0, you would evaluate using multiple corrupt example like x1 to x5, and when you average, you get something like the blue line instead of the yellow negative gradient. So that's roughly correspond to what you think would be the saliency of that feature. Okay, so that's for smooth grad. If you apply in computer vision the same example, you should see that there's less noise happening on the sky, on the cloud, and more saliency is sort of concentrating on the obelisk. Okay, so there's another method called integrated gradients. This involves a little bit of calculus, so I'm not going to go into the very details of this method, but I just aim to give you some kind of high-level idea. So the problem they're trying to solve is this problem of feature saturation, in that if you optimize your network so well, such that when you feed in the input, most of the feature will get zero or like very small gradients. And they propose, they actually, like from their analysis, they show that this is not the best case to deploy this kind of gradient-based sensitivity measure. So what they do is that you define a baseline, which is basically some input that carries no information. In the sense of computer vision, you can pass in like an all black image or all white image. Either would be fine. And then what you do is that you also construct multiple versions of input. But what you do is that you construct an interpolation between the original input that you care about and the baseline. All right? So basically, in this example, the original input is this dog, and the baseline is this black image. And then an interpolation would be like a darker version of this original dog image. Okay? And then you basically also do some averaging over different versions of gradients, and you actually average by a kind of integration. I'm not going to the detail of that integration, but this is a high-level idea. Okay, so if you apply integrated gradients for that, you get reduced noise on the sky, but you still get some noise on the clouds. So, I mean, it seems like it's doing something, but just pretend it's fine for the moment. All right. So that roughly wrap up the first part of this talk. So to summarize, I talk about two different goals for interpretability. The first thing is about building a transparent model that gives you easily explainable behavior. And this explainable behavior does not depend on any kind of output of the model. Whereas the second way I talk about this post-hoc interpretation will keep the original model intact, but rather you will do some interpretation that depends on the model output. Why do I talk about all this kind of stuff? How this is related to the next stuff I talk about? So the first piece of work, which is about uncovering word alignment from UMT, this work is basically comparing a specific kind of transparent model versus a post-hoc interpretation that we apply under a specific user case that I guess a lot of people here would care about, which is UMT. And the second thing is about comparing different post-hoc interpretation method in a rigorous quantitative way to get some idea of how this interpretation method actually works for NLP models. So before I move on to the next section, any questions here? No? Okay. So move on. So, all right. So I guess most people are probably familiar with this material, but let me just recap. The problem of word alignment is that you are given a sentence pair, where the sentence pair are like a translation of each other. In this case, it's German to English. And you're trying to find some correspondence between the source words and the target word using the relationship of like whether they are word translations of each other. So the correspondence for this example would look like something like this. Okay? So let's just apply this problem using the interpretation view that we just talked about. So you can view this as a model transparency problem, right? And in this case, some people argue that, attention in this case would be a transparent model in that you can interpret the behavior of the model using the attention weights. But there's just a problem here. So suppose we are in the middle of translation where we translate we, the second we, and we're about to output the next word. So in this case, you can, given the source input, you can either output only or should. So a good model in this, at this stage should both look at the word nur in the source, on the source side, which means only, and the word resultant, which means should, right? But the problem is that when you do word alignment, you actually have the output. So your word alignment should really depend on the specific output choice that you have already made. So maybe model transparency in this case is not the best way to do this. And we are going to show this like empirically in the experiment section. All right. So the next thing is about doing post-hoc interpretation using standalone models, which is basically I want to build another model that models the distribution of the alignment pairs given the source and target sentence, right? And apparently this is something that people have done for a long time, like back in the era when people still use the SMT system, they would use Giza or Fastline to come up with alignment for a parallel corpus. Okay, and what we care about here is that we want to do this post-hoc interpretation with perturbation or like a relative sensitivity measure. So basically in this case, given this input, which is already mapped into an array of word vectors, what we do is that we want to add some perturbation on the source side, and correspondingly you get some perturbation on the target side, which may change the word should, which may change the argmax output, but still, if you care about should, you should take gradients with regard to the prediction score of should. All right, so that's the 3 views. But now we have a problem. I keep glossing over this term of feature, right? And now is probably a good time to look at that in a more detailed way. So if you think about the notion of feature in computer vision, it's pretty clear because if you zoom in the image, if you zoom in any image large enough, you will see individual pixels. And you can just very naturally use these pixels as input features. And when you compute gradients with regard to input features, you can just compute gradients with regard to pixels, and you get some saliency map that we just showed you, which is straightforward. However, if you think about the same problem in NLP, the input feature here is a word embedding, right? And you might say, well, it's pretty straightforward to compute saliency for each dimension of embedding as well. But if you think about it, what we really want here for the word alignment problem is that we want one saliency score for one word, right? So you have to do some kind of composition over the saliency score of each dimension of the word embedding to come up with the saliency of a word. How would you do that composition? Well, here's what a previous work do. So this work by Li et al. Basically did this formalism where, okay, so for this formula, all the symbols are scalars, okay? And y is the prediction score of a certain word at a certain time step. And EI is just one dimension of the word embedding. So basically what it's doing is that it's computing the absolute value of the gradient of the word embedding and then just average it, okay? And because of the absolute value that's been done here, the range of this value is really from 0 to positive infinity. Just keep that in mind. We're probably going to revisit that in a minute. Okay, we want to do something different. Okay, so here's our proposal. If you consider the word embedding lookup operation as a dot product between the embedding matrix and the one-hot vector, all right? And then if you think about what that one-hot vector really means, we can really say that the 1 in that one-hot vector denotes the identity of the input word, which is basically saying, oh, this input word corresponds to this item in the vocabulary, okay? And what we want to do is that let's just treat that one as a real value, and let's protect that one, which is by saying that what I'm actually doing is that I want to take gradients with regard to that one in the one-hot vector. And if you do some math derivation to figure out what it actually means mathematically, you come with something like this. So this is basically doing a weighted average over the gradients of the word embedding. And then the weight of this weighted average is the original embedding value. And just to keep in mind that in this case, the range of this saliency scores from negative infinity to positive infinity, which is different from Li's proposal. All right, why is this different matter? So recall that example where I showed you that for a certain time step, you could either output the word only and should, okay? There are places during translation that an input word may actually strongly discourage certain translations. So in the example of only and should, these two words are actually contradicting each other because you can only put one word over there. So if you choose the output word should, the source word that corresponds to only, we actually carry a large negative gradient because it's discouraging this output, right? So if you ask me, okay, is this word only a salient word? I would say yes. But in terms of word alignment problem, should they be aligned? No. Because should and only are not like translation of each other. So really, what you really need is a polarity of the saliency here for each of the individual words. And so basically, if you do something like absolute value, or you compute error to norm of the saliency of each dimension of the embedding, you actually fall into this pit where you get some value, you get some magnitude, but you don't get the polarity. Okay, and we're gonna empirically show that this actually matters in actual practice. Okay, so before we look at experiments, I want to talk a little bit about evaluation. So in general, if you ask people about, oh, I want to evaluate this interpretation, people will give you really weird looks, because most people would think that interpretation is a pretty subject thing, where like maybe if you ask different people, they'll also give you different interpretation of a model output, right? But fortunately for this case, we're actually in a better situation because word alignment is actually a problem that we care about, and people have built human judgments for word alignments given certain sentence pairs. So we can rely on these human judgments to evaluate the quality of our interpretation. But there's one more caveat, which is saying you only have human judgments for certain source and certain reference, right? You cannot get human judgments for any kind of model output. So what you need to do here is that you have to do force decoding to force the NeurMT system to generate the reference sentence that we have human annotations of. So this will have a small risk in that sometimes if you force the model to generate something that's really unlikely, you probably push the model into some wild region where it's not trained to do. But we actually did some comparison using free decoding, which is we just let the model to generate whatever it wants. And roughly saying it's pretty much fine. So here for this presentation, I'm just going to present the results with force decoding. If you're interested in the free decoding results, you should read our paper. All right, so let's look at experiments. So we experiment with convolutional sequence-to-sequence model, LSTM, and transformer translation model. And the data set we use is following Zenkoda 2019, which is the data set that covers German English, French English, and Romanian English. We actually did experiments for both directions. So when we apply smooth grad, there are two hyperparameters we have to choose. One is the number of samples you take for the saliency evaluation. One is the Gaussian noise, the variance of the Gaussian noise you have to impose on the input. So these are the choices we made there. So here are the baselines we compare with. Naturally, we want to compare with attention weights, but we also want to make sure that this very operation of smoothing does not improve the performance by itself. So we also did smooth attention, and that will corrupt the input in the same way as smooth grad. And then we average the attention weights obtained using these corrupted input. We want to compare with Lee et al. 2016, and we also want to verify that, like smooth grad won't how does Lee method perform under the smooth grad method. All right, so here are the results. So we are presenting alignment error rate here. And for this metric, lower is better. Okay, so if you look at the performance of attention, looks like that. If you do smoothing, it does not do better. Actually, I do cite it worse. If you look at the performance of Lee's method, it's roughly the same as attention. But if you look at our method, without any smooth grad fancy stuff, it already does better than both attention and Lee's method. And if you use smooth grad further, you can get further, even better performance. Now, here's an interesting part. If you compare our method with FastAlign, which is a model that is trained to do this kind of interpretation, we actually do slightly better there. This is actually notable because FastAlign, as I said, FastAlign is a model that's trained to do word alignment. So all the parameter in that model is optimized to do this interpretation task. Whereas what we are doing is that we are trying to interpret a model that's trained to do translation. So it will learn some alignment knowledge, but it's not really optimized to do that. But yet, by doing that interpretation, at least for convolutional sequence-to-sequence model, we are able to do better than Fast9. So that's notable. But honestly, if you look at stronger standalone interpretation models, such as adding an extra module to do alignment on top of transformer, or if you deploy Giza++, which is a slower but stronger alignment model, we're not doing better than that. All right, so that's one group of results. So if you look at the attention weights across from different architectures, you see that basically convolutional, the attention output from the convolutional model performs best, and the transformer is pretty noisy there. And if you compare the results from our method across different architectures, you get pretty significant decrease in alignment error rate, but still our method is not strong enough to fully bridge the gap between different architectures. And you still get the same ranking in terms of architectures. And also, only convolutional model does better than all of the standalone interpretation models. Whereas if you use something that's noisy from the start, you're going to get worse result on top of that. Okay, so here's some examples to give you some quantitative idea about what our method is doing. So basically, the vertical axis here is the source. The horizontal axis here is the target. And because it's alignment, so each column is normalized to sum up to 1. Okay? And you probably don't trust me, but all of these 3 grid scale plots actually drawn under the same scale. So basically, you can see that our method generates more peaky interpretation of the output, whereas if you compare Lee's composition method with attention, they're doing pretty much the same thing. And I want to highlight one point here. So for this reference we are looking at, it didn't translate the source word, English, the German source word nur, which means only. So if you look at the reference, you don't see only there. However, both attention methods and Lee's method align some words to nur at certain time steps. Okay? Whereas our method, it's trying to align something, but generally it's cleaner compared to the output of these two methods. So this is to say that our method is much more robust to these kind of contracting choices of words on the source side. Okay, so to summarize, I talk about 3 different kind of interpretation methods to tackle this word alignment problem. So you can use attention, which gives you maximum transparency about how the model actually works. But the only problem is that people cannot really understand that, because if you compare that to human judgments of a word alignment, it does not really agree well in that you observe a very high alignment error rate. And you can use standalone alignment models, which give you the best possible word alignment, but has nothing to do with the translation model. So if you want to do error analysis on the translation model, this is really not your choice. Whereas our method is sort of a combination of both words. On the one hand, you get some exposure to the model, because when you evaluate gradients, you depend on the model to do that. And on the other hand, you get reasonably well word alignments. So as humans, you can actually understand what's going on there and probably discover some patterns. So before I move on to the next piece of work, any questions here?
Yeah, I have a question.
Sure.
So in your formulation that you changed from Lee, the thing I'm constantly struggling with that is why you are actually multiplying the activations, the embedding scores, and the gradients, right? So you are doing this, if I'm not wrong.
Sorry?
You are multiplying the embeddings and the gradients. So why does that actually influence polarity? Because isn't the distribution of positive and negative values in the embeddings more or less random?
Right. But if you have a negative input,
Yeah.
and you have a okay, if you have negative input and you have a negative gradients, that's basically saying you want to increase the magnitude of that level. Basically saying you want to push it even more negative.
Yeah, I can see how the negative value goes through the gradients, right? Because
Okay.
the rules for automatic differentiation tell you that the multiplier gets passed through the backward step. But why does it matter when you go forward? Because you perturb this through whatever weird activation functions you have in there, which might not be homomorphic to multiplication, right? So
I don't think I'm following.
yeah, so yeah, I'm not sure if I'm making any sense actually.
I think all these signs are basically arbitrary, right? When you can flip the signs of the embeddings and flip their corresponding signs in the first layer of matrices or something like that.
It's just that the arbitrariness worries me, because does it actually mean anything? So
No, it doesn't, and that's why you cancel it out here, right?
Okay.
The sign between the gradient and the parameter cancels out as a consequence of this arbitrariness. The signs arise out of that.
Okay. I still don't understand it, but I'm going to accept it.
I mean,
Well,
yeah.
like mathematically, it's just a chain rule,
Yeah.
to be honest.
Yeah, I see this in the backward step. I'm just wondering what's going on in the forward step, because I don't see the meaningfulness of the sign when you go forward, right?
No, actually, like in the forward step, it doesn't make any. Yeah, it doesn't, like the negative and the positive values doesn't make any difference. It's just arbitrary.
It depends on what you multiply it with in the next layers, right?
Yeah.
If those are also negative, then they have different meaning compared
Yeah,
to...
but you also have things like rel, which is canceling out anything that's negative, right? And so on and so on.
The rel has been learned to match the corresponding input, right? And if it wanted to go the other way, then the input below would flip the sign.
I don't think the sign means anything in an intermediate step, but
Yeah.
the point he's making is when you go completely end to end, it does mean something. Right? If you're starting from the word all the way to the because at the output it does mean something.
I mean, it makes all the difference, right? I'm just deeply worried that I don't understand why that makes all the difference. Okay, thank you.
Any other? Yeah.
So you're concentrating on saliency, that's the sensitivity of the input to the output, right? Sometimes you actually want to know how jagged the sensitivity is, as well how bearable the sensitivity is.
You mean like when you change it by different magnitude?
Yeah, like so you've kind of averaged out to get some kind of gradient. You
Right.
actually sometimes you actually want to know if it's difficult to achieve the jaggedness.
Okay, so in terms of that smooth grad thing, so there's you're probably aware that there's a Gaussian noise that's applied to that, and there's a variance term, right? So when we actually tuned that a little bit, if you look at the paper, but we are actually a little bit surprised that we actually end up using the same parameter as the author, like of the original paper, and the original paper was using an image classifier to evaluate their interpretation methods. So I don't know whether that's a coincidence or there's just some sort of interaction between human cognition and the saliency of the neural networks. But yeah, I think that's a good point. But here for us, we didn't really try to change a different magnitude. When we tune that parameter, we barely optimize for best word alignment quality. So that's what we. Right.
Do you have an intuitive explanation why the alignments work so differently for convolutional and transformer and what was the other LSTM?
All right. So we have something by the end of the next section. But yeah, I can answer that question now. I think it's mostly depth.
Oh, okay.
So basically, if you for transformer, you build a 6-layer transformer, whereas I think the convolutional model, both the convolutional model and the LSTM model was like 4-layer, 2-layer. I don't quite remember, but like something shallower. So basically, if you have a longer computation chain, there's just more noise.
spread out more.
Right. It just spread out more.
Yep.
I don't have the alignment map for transformer here. So this is for convolutional model. But if you look at LSTM and transformer just everywhere. It's not as concentrated as here.
Multi-head transformer?
This is a multi-head transformer. I think it's 6 layer, 8 heads. Yeah.
It's everywhere for the attention. It's also
right.
It's spread, but it's less spread out for the gradient-based method.
Right.
Okay.
But if you pop up a level 2, so the point you're trying to make is that this word alignment is a test case for interpretability.
Right.
So, so what does that mean? And when you say that, okay, if I have a deep transformer, I don't get good word alignments. So are you saying basically the transformer is just not interpretable no matter what because it's too deep, or this method is the wrong method for trying to interpret what transformer is doing?
I would say, oops. I would say it's mostly the limitation of the interpretation method we currently have does not work for these deep models yet. Or like deep and with like multi-head attention, whatever.
But the
that people
principle, like, if you look at the nice, clean end-to-end math, it doesn't seem to depend on how complicated the box in the middle is.
Exactly.
So there's something wrong with the intuition behind why this like, you know, there's like this is a very nicely intuitive sort of idea of interpretability, but basically you're saying it doesn't work in the more complicated cases because there's nothing intrinsic to the method that tells you why it would be more
noisy.
Work better or worse depending on the complexity of the model, right? Because the whole point of the method is that all of the complexity of the model has been squished into, well, I don't really care, I'm just taking the grade.
Exactly. That's the hope. But still, like if you look at the salient, like the vanilla saliency, where you just take the gradients, like if you look at any saliency map that's generated in computer vision, it's pretty noisy, to be honest.
Did you look at the, like you had this smooth grad and then the integrated grad, like if you tried to be, like vary the hyperparameters of that and like do like massively more smoothing or more integration, did that make a difference?
If you do massive smoothing, like if you apply noise with very high Gaussian noise, it's going to be everywhere. Yeah. So it's not meaningful at all. Basically, you just like intuitively, you're just make your input really vague, such that it does not carry any kind of meaning there. So yeah, I would say there's a discrepancy between what we think this method would give us with what it actually gave us. And unfortunately, I would say like the discrepancy is still, like, why is this discrepancy still occur is the open problem. And but on the other hand, I don't think a lot of the existing interpretation research actually like look at that problem pretty rigorously. So that's actually part of the problem that I try to solve in the research that I'm going to talk about in a few minutes. Any other questions? Okay, I'm going to move on. All right, so the second piece of work, this is actually ongoing work, so I would appreciate if you give me some feedback on this. So this is about building some benchmark for interpretations using the existing linguistic annotations. All right, so when we saw the alignment results, we were actually pretty encouraged and say, hey, let's just use this for other NLP tasks that we care about. And let's be honest, we are not really the first one to apply these kind of methods to NLP tasks. There's work on text classification, basically roughly the same as in Vision. You build a text classifier, you want to figure out which part of the text contributes to the prediction of this class label. Is anything going on? Okay. there's the sentiment analysis where you want to figure out which source word are carries positive sentiment, which words carries negative sentiment. And there's question answering, which is saying, okay, which part of the document you look at to find out the answer for the question. Okay, so all of these work give you some insight about each individual task that they care about. They sort of generalize some pattern. Oh, the model is doing this, the model is doing that, the model is like looking at certain things to make decision. So, but there's a underlying assumption that's going on here. Basically, you're assuming that by doing this post-hoc interpretation, you know this is how the model actually make the decision, right? But is this actually the case? So let's do a quick flashback on the word alignment example. So basically what you do here is that given this target word prediction, you're trying to figure out which source word is the most salient words for predicting this output, right? Yeah, you're trying to figure out which source word is the most important word for predicting this output. So if you just think about this a little bit, you have the source, you have the target, you have the model. How many ways could the model make the decision? Well, if you have different model will make decisions differently, right? If you have a different input or like you're predicting a different output word, the model will probably make decision in a different way. But with all of these factors constrained, there's only just one factual way that your model can make the decision. And yet, when you look at, if you compare like different interpretation method, like the Lee's method and our method, you actually see like very different interpretations out of this interpretation method. So what I'm saying here is that these interpretation method output are really just different perspectives of one factual interpretation that like it is purely conceptual. We probably cannot see it, but a natural question we want to sort of ask is that how far are these perspectives to this factual interpretation? And you should feel alarmed about if these perspectives are actually far from the factual interpretation, and you draw a conclusion from these erroneous interpretations, you may get misleading conclusions at the end, right? So the research question I'm really trying to answer here is that how can you quantitatively test the effectiveness of these interpretation methods in the context of NLP? And moving forward, when you see different kind of level of effectiveness of this method, what kind of factors are these effectiveness correlated with? Like, are they correlated with model size, the performance of the end task, and the architecture? So in computer vision, again, this is actually an easier problem because let's take the image classifier example again. The reason I say it's easier is because they would have ground truth, human annotated ground truth for their image. For example, I think this is the image classification for a medical application. What you get here is that you're trying to ask the image classifier to predict, given this X-ray image, does this person have any kind of disease? And you can generate some kind of interpretation by a human, basically saying, there's a tumor in this X-ray, so this is the cause of this disease. And alternatively, you can use different kind of interpretation method to generate a saliency map with regard to this prediction, and get a distribution of the feature saliency on this map. And then you can compare these interpretations with the human judgment to get an idea of how well this kind of interpretation is doing. Okay? But for NLP tasks, the major problem we are faced with is that we don't have ground truth interpretation like that. So what we hope we'll do is that, we actually build a lot of linguistic annotations for different kind of NLP tasks. Can we leverage these existing annotations to use them as some sort of this ground truth interpretations? So the case we look at is this lexical agreement case. We studied this case because this is actually frequently studied previously for this interpretability research. But however, when you look at this research, they're actually a little bit different from what we are trying to solve here. What they're trying to do in these papers is that they concentrate on evaluating this kind of probing task performance, namely, given a prefix or given a partial sentence that captures the first part of the lexical agreements, can you predict the other part of the lexical agreements properly? So let me illustrate this with the example of subject-verb agreements. So basically, you have this prefix. And I can tell you that following this prefix, there's a verb. And the lemma of the verb is look. So given this prefix, would you choose to predict look or looks? Well, let me give you some hints for this. There are several nouns you probably want to look at. You probably want to look at people. You probably want to look at footage. You probably want to look at Bronx and decide which of these verb should the number of your verb be agreed with. Okay? And I guess for most humans, if you're like an adequate English speaker, you should be able to figure out that you should look at people, which is the real subject here corresponding to the verb, and that to agree with the morphological number of people, you should predict look. Okay? This is what I call as probing task. All right? And that's what previous people do. Now, the problem I care about is a little bit different. So assuming we have a model, and the model think, oh, look is more proper words in this situation. In that scenario, which of these nouns should the model be looking at? Or if you do some kind of interpretation here, which of these nouns should the model assign the most saliency for? That's one case. And the other case is that if the model thinks, oh, looks is more possible here, is the ground truth going to change corresponding to that different prediction? So basically, following this intuition, the test is constructed in this way. So I'm going to look at the saliency for the word people and footage and Bronx here, right? By interpreting this prediction. Suppose it's look. In the case of its predicting look, which is the correct word, I'm going to ask the following question for this interpretation. Does the saliency assigned for the subject people higher than any of the other nouns which I would call as attractors? Is the saliency assigned for people higher than any of the attractors? If it's high, then I'm going to say, oh, this is a good interpretation because it agrees with human intuitions. Whereas if the model predicts the wrong verb, I'm going to say, oh, for one of the attractors, which has agreeing morphological number as the verb there, the saliency for one of the attractors should be higher than the saliency of the real subject, people, which has a different morphological number.
We're thinking of this as an evaluation method. You would not only ask, is the model doing the correct thing, but is it doing the correct thing for the correct reasons?
Exactly.
That's nice.
Yeah, and I mean, in this case, the reason I design different tests for different prediction is that I want to separate the interpretation from the prediction of the model. Because I don't really care about the prediction of the model. I care about, under any kind of prediction, kind of interpretation method give me a good interpretation of this decision. Yeah, and it's good in the term that does it align with human judgment? Because that's the best ground truth we can get. If you don't agree that, well, human judgment is the ground truth in this case, then it's going to be tricky.
For that, like challenge test sets, basically. This is a false decoding task, I suppose, and you are checking if it's doing the right thing in the right way. So you can rank models by this, essentially.
Wait, what do you mean?
Let's say you have two different models, okay, and they both agree that looks is the right thing.
Okay.
But let's say one of them has higher weight on people than the other one. So would you then say that the one that is judging people to be the better feature, a better model?
Are you holding the interpretation method constant?
Yeah.
Well, I meant, look, so it's predicting the correct thing, but it's also assigning more weight to the correct reason for predicting the correct thing. So that would be a better model in an evaluation setting.
I would be cautious about saying that.
I mean,
Yeah.
it would be better for subject-verb agreement, but who's to say what it does for any other particular phenomena?
Yeah, but let's say that you have a large test set. So my question is, because we are now getting, let's say for machine translation, we are getting to areas where we're having really good translations everywhere. So maybe the models aren't making mistakes anymore. But maybe you still want to rank them, so maybe you should choose now among the models which are not making any mistakes anymore, the one model which is not making any mistakes for the right reasons, right? Because you can't measure it quantitatively anymore. Huh.
Right, and to make a comment about shortcoming, it is true that we only focus on one kind of specific kind of phenomenon here, but the situation we are faced with is that you only get annotation, human annotations for certain kind of phenomena. That's one thing, and the other thing is that you'll only get a clear ground truth for some of these phenomena. And just to reflect back on the previous piece of work about word alignment, the reason we don't want to evaluate these kind of interpretation on the word alignment data set, which we also have human judgments on, is that if you actually look at these human judgments, they're pretty noisy. And I personally done some annotations for people who will give me some translations and say, okay, can you align the Chinese words with the English words? And a lot of times it's really hard because a lot of these translations are for example, if you're translating some Chinese idioms into English, right? How do you align the words? You will want to, the phrase alignment is pretty clear because you can align this span with this span, but talking about individual words is really not that easy. So you end up doing some arbitrary stuff when you're doing that annotation, which causes the human annotation for alignment pretty noisy. So that's why we don't want to use that task for evaluation. Whereas here, when you talk about subject-verb agreement, you always get a pretty clear ground truth, even amount of people with relatively higher inter-annotation agreement, which is why we think this is a good task to evaluate this kind of phenomenon. It's a pity that we cannot do this for a lot of the other tasks, but again, this is a best effort of trying to pin down what is a good interpretation method. As I said, it's a difficult problem because a lot of times there's a lot of subjectivity associated with the kind of interpretation. So it's actually pretty hard to evaluate. Yes.
Going back to this question of model ranking, I'm still thinking evaluation. Let's say the model makes a mistake, like looks. Would you say it's better if it makes the mistake looks and assigns the highest saliency to people, or if it makes the mistake looks and assigns the highest saliency to footage? Because if it looks at people, it shouldn't have made the mistake looks, right?
Right.
If it looks at footage, it might have made it, but it's still wrong.
Oh, footage is singular too.
So I don't think this work is trying to make that judgment, to be honest. You can come up with a limited number of these tricky questions, but I wouldn't make judgments on that.
Okay, so in falseness, there's no difference. Okay, so you can do that. Fine. Right.
Well, I mean, it seems there are two independent pieces of knowledge here, and they argue in different directions on that, because one piece of knowledge is where is the controller of agreement, and the other one is, given the controller, what is the right agreement form? And so, obviously, they aren't both intact, and one could be off, or the other could be off, and it's not clear which is going to be the better mistake.
Yep. But anyway, this is not trying to actually solve that problem. Like, we are not trying to compare the model. We are trying to compare how does interpretation method do with these models.
Yeah.
So, should I move on? Any other questions? Okay. So, under this, oh, sure.
Make a comment about the difficulty you were referring to of doing alignment.
Okay.
Because it's really an ill-conceived task to ask people to align words. Syntax is not about words. As you said, it's about phrases. And so it's asking people to do something that doesn't really make sense. And no surprise that people don't necessarily all do it the same way. And here, it's not entirely different either, because you don't agree with a word, you agree with a phrase. Like if we had a sentence, 2 deer, blah, 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 were seen, or 1 deer was seen. So what's controlling the agreement between was or were? It's whether the phrase 1 deer or 2 deer is plural or singular, and the word deer has the same form. So what's the right answer for what word is controlling agreement there? It just is the wrong question.
That's a good point, yeah. So I think for this specific test that I'm constructing, I'm looking at the head of that phrase. But yeah, you're right. Like for cases like deer, you cannot really tell the difference. You have to look at the whole phrase too. So agree, yeah, there is discrepancy there. But again, like this is like a best effort we can do to like do some kind of evaluation for these interpretations. Okay, right. So under that framework, we constructed 2 test sets based on the existing human annotated corpus. One of them is constructed using Perturbation because it annotates the syntactic structure of the sentence, so we can know which is the subject that corresponds to certain verbs. And in that case, for one verb, you might get multiple attractors in the source sentence, because there might just be multiple nouns with different numbers compared to the verb. Okay, and the other one is this what I call synthetic evaluation, which is constructed by Marvin and Linson, 2018. So this is basically a synthetic test that was initially designed to make the language model fail. So there is constructed with a lot of like purposely confusing sentences to try to identify the boundary of the capability of the language model to conduct this subject-verb agreement task. In this case, because it's synthetic, there's always just 2 verbs in the sentence, one subject, one attractor, and so in that case, this is a sort of a cleaner and easier case to evaluate. And we actually also want to do another one with not only like syntactic relations, but also some semantic relations. So we also want to look at this correct resolution data set, where like when you predict a pronoun, you should probably be looking at the corresponding entity dimension that has the same gender as this pronoun. We are still working on that. Talk to me if you're interested. So, okay, let's look at some experiments here. So the model that we're trying to interpret is, as you can probably guess, is a language model. But we did a little bit modification on the original language model here, in that we replaced the final linear layer with one that's fine-tuned to predict the specific agreement of interest here. So in this case, it would be subject-verb agreements. The reason we do this is that if you just interpret the word prediction score, it may introduce some kind of out-of-scope agreements such that the word choice may be associated with some kind of semantic relations or whatever, which will interfere with the evaluation. Okay, so the architecture of language model we interpret here are LCM language model, trained on Wikitext2, QRN model, which is basically a convolutional language model, but it's designed to imitate the behavior of the LCM language model. also trained on Wikitext 2. And we also did experiments with transformer with adaptive input. This is a pre-trained model on Wikitext 103. And interestingly, we tried to train transformer language model on Wikitext 2, but we're not able to do that. And I actually asked around, like, seems like among the community, this is something that's like no one is able to do, and no one knows the reason for that. I have some hypotheses if you're interested. We can talk later. So all the fine-tuning that I just said was done on Wikitext 2. And the fine-tuning process is actually pretty easy because if you're doing subject-verb agreement, you basically do some post-tagging to decide the morphological number of the verb, and then you just fine-tune to predict that tag. Okay? Right. Now let's talk about the probing task performance, namely the performance of the model to predict the morphological number of verb, like how many times, what's the fraction of time it gets the form of the morphological form of the verb right. So this is different from the interpretation evaluation that I just talked about. So basically, we did the two data set. This is Perturbation, and that is synthetic evaluation. So as you can see for Perturbation, because it's slightly more in-domain, and that is just a newswire text, our model just do better in terms of probing task performance, and basically transformer does the best, and the other model is slightly worse on that. And in terms of synthetic evaluation, because it's out of domain synthetic, as I said, you actually do pretty bad on that. Like you can see, like for LCM, QRN, they're actually lower than 0.5, which is basically worse than random. Okay. So now let's look at the interpretation quality, which is you do interpretation and compare with the ground truth that we constructed using the human annotations. So basically, the vertical axis is still like the fraction of times the interpretation passes the test. And we also do pen and synthetic evaluation. I mean, like the interpretation method we experiment with are roughly the same as we did for word alignment. And just to explain this random thing, this is the case where, depending on the model prediction, we use a random value saliency of the words and evaluate that. And for synthetic evaluation, it's pretty clear that it's 0.5. But for Perturbation, it's lower than 0.5 because if you get the prediction right, you have to assign more saliency on the subject to pass the test. So in that sense, it's actually a slightly more constrained case for evaluation. So if you do random, you're actually going to do worse than 0.5, which is what's happening here. So basically, you can see that, again, Lee's method is sort of lagging behind compared to our method. If you look at different architecture, if you look at QRN, and if you look at transformer, you can generally see that our method plus either smooth grad and integrated gradients does the best than the other method. But another interesting trend is that when you switch from the previous two smaller architecture to the pre-trained transformer architecture, you observe a pretty steep decrease in terms of interpretation quality here. So what is happening here? We had two hypotheses. One hypothesis is that if you have deep model, it will probably hurt interpretability. On the other hand, there is some study in the MT literature which is talking about, if you have too many heads hovering around, it will hurt it will probably do not much about the transition quality. And we thought, maybe these heads are hurting interpretability. So we had this state-of-the-art model, which is pre-trained by Facebook. They have like 16 layers and 8 heads. What we do is that we try to reduce the number of layers and the number of heads. So this is the same results I just showed you now. And this is a reduced layer, a depth and head model. This is a reduced depth model that we train. So we compare these models. Just by reducing the number of layers, you already get a pretty steep boost in terms of interpretation quality. And when we further reduce the number of heads here, for some reason, it's affecting the performance of Lee's method a lot. But for our method, it's pretty stable. And to our surprise, when we reduced to 2 heads, like the performance actually got worse. We actually have some other results with different kind of number of layers, like 8 layers, 2 layers. And the consistent trend is that the number of, like changing the number of heads does not really have a large impact on the interpretation quality. So it seems like the depth is a major culprit here.
Like cheating, doesn't it?
Sorry, why is that?
Because you're not telling us how much performance you're giving up by choosing the smaller models, right?
You give up.
Yeah, exactly. So
Right.
you are not interpreting. So you aren't interested in those small models. You're interested in the big model.
Okay.
But you can't show what the big model is doing, so you're backing off to a weaker model. What exactly is this telling you? Not much at this point, right? Just that you don't know how to interpret the big model.
Right.
Right. That's basically the conclusion.
Okay.
Yeah.
Yeah. If that's a question, that's an answer. Then it's good.
Yeah.
Okay.
I'm not saying like these models are. Again, I'm not making judgments about the model.
Yeah.
I'm making judgments about the interpretation method.
Right. And the conclusion is it doesn't work for
It doesn't work for large models. Yeah. I'm not saying like the smaller model is better because it's more interpretable. That's not the argument I'm trying to make. Okay. All right. So just some quick qualitative checks before I wrap up. So we were wondering, are these interpretation methods just keeps looking at the immediate previous words? And actually, they are not. So this is the same example that I showed you previously. And you can see that in terms of, if you look at the smooth grad, it actually assigns most saliency on people. And in terms of integral, for some reason, likes however, but still, if you compare these 3 nouns, it's still like people still get the most saliency here. And if you look at the interpretation we get from different models, intuitively, different models should make decisions differently. And if you compare these interpretation from different models, they are actually pretty different from each other. So in some sense, it's a good thing because we know that we are getting some exposure about the model.
You were correlating interpretability with depth. Does depth correlate with performance in
Yes.
your cases? So isn't it rather that interpretability might be negatively correlated with model performance than with depth?
Good question. That's the experiment I'm grading right now on the grade.
So basically, the better the model, the harder to tell what it's actually doing.
Sounds familiar.
Maybe.
Possibly. Depending on what you find out. Okay.
Depending on what I find out.
Right.
Yes. Yeah. So the way I'm testing this is that I'm going to train the same model with different amount of data.
Right.
So if you reduce the amount of data, you would do worse, right? But you still have the same model size. So in that sense,
Kind of the same thing. The better the model, the harder it is for us to evaluate, even, right? So maybe you're just looking at the same phenomenon from a different. You're looking from the bottom of it, while you're looking from the top, and you're just seeing the same things.
well, I mean, it's a good thing in
Yeah.
some sense, right? Because
Well, yes and no. It's causing its own set of problems for us, but
but like from my perspective, I want to know like how
Yeah.
these interpretation method works. If that verifies what you see from like day-to-day production,
yeah,
it's a good thing. I mean,
Yeah.
their behavior is sort of predictable. It's not like random stuff, right? Okay, so just to wrap up this part of work. So basically, we want to use Lexical Agreements to do rigorous quantitative checks for post-hoc interpretation, and we see that it does open up some possibilities to do that. And you can see, again, our proposed method together with smoothgrad and integrate gradients works the best consistently. And as we repeatedly made the point during the discussion, deep NLP models are still sort of out of reach for existing interpretation methods. So there's some open research to be addressed there. All right, so just briefly covering some of the future work that I kind of want to do. So one thing is that we probably want to design some better interpretation method that actually works for deep architectures in NLP. And the second thing is that here we are basically evaluating some interpretation method. How can we use them in the real-world applications? For example, if we want to do some kind of quality estimation for MT models, if you know better about the internal decision mechanisms of these models, does it give you more insight to estimate the quality of the output? And also, can we use this interpretability, these insights from interpretability, to improve our models? And lastly, there's a ongoing interest about like using different kind of interpretation method to probe certain linguistic properties in these kind of large pre-trained language model. And I think probably if you borrow some of these interpretability method from computer vision, you can probably do something with like these line of research. So
I have an experiment for you. So you're doing this with different types of data, and you're trying to make your deep models worse, right?
Right.
Instead, make your shallow models better. Teacher-student training.
Oh, okay.
Train a student which has lower depth than the teacher, but is nearly matching it in performance. It's also emulating the teacher's probability distribution and everything.
Mm-hmm.
If that thing is easier to interpret, then you have a case, right? Because I'm always vary when you make things worse and then try to say something about it. I think it's better to make things better than try to say something about
Good point.
it, right?
But if you can interpret the teacher, what does that say?
No, you can't. If you can't interpret the teacher,
if you can
but you can interpret the student,
Right.
and the student is modeling a very similar probability distribution to the teacher, then it's not quality bound, and you can at least say that it's depth, but not performance, right? Because the question is, does the interpretability correlate with good performance, or does it correlate with architecture? If the student has the same performance, but easier architecture, and it's easier interpretable, then you have, I think, removed the performance angle.
You could do a third one, which is to train a student with the same architecture as the teacher. Not a reduced architecture.
Yes, I mean, this all goes in the same realm of experiments, right?
That would be very interesting.
Yeah.
Because the data the student's learning from has been regularized in a very interesting way, and maybe that improves interpretability.
anyway, that's my last slide. Thank you.
Question?
Yes.
Say, for example, I find that there is like a model does a bad thing. Is there a way for me to trace that back to the training data and say that, okay, these 10 examples in the training data are the ones that made the model do this thing?
No. That's a short answer, but
Yeah, because for image classification, there seems to be some research that way that you can, like, given an example, see where, given like a result of classification, you can kind of look at which images in your training data like, activate like that class most, and you can kind of like, rebuild like that.
in that case, do you have to retrain the model using the examples that you care about? Is that something that's happening there?
Not necessarily, but you can like trace it back to like which images made the model like tip that way.
Okay.
I would still say that you can't do that. You would just need to have examples where it went wrong, right?
Yeah.
Or maybe, I think the problem might be that you also would need to have ground truth where it's right, but the model doesn't like it for some reasons.
Yeah.
So I guess that's hard. With images, it's easier. Because we saw those medical images where it was very clearly highlighting the enlarged heart or something like that, right? So that's easy. But for language, I would have a hard time to construct similar minimal pairs.
One example, for example, like doing like say grammar correction or like monolingual rewrites. Sometimes the models just generate like a token that's like I don't know why it got that. Like for example, it's talking about cars and they generate something about I don't know houses or something. So you can like maybe trace back that token in the training data, like learn some kind of paraphrase somehow.
Okay. I have a hard time like trying to form a way of how it works, but
because you only get your gradients on the source, right, or on its history. You don't get the target part that led your model astray. So let's say you have a training pair, correct source, incorrect target.
yes.
So the incorrect target isn't manifesting in your error tracing method anywhere when you do this.
It's true.
So you do not know what pattern to look for. You only find a pattern what to look for on the source, and you might find that, but you are not seeing the incorrect target that made your model learn the incorrect thing. Right? I guess that is in your way. Unless it's somewhere in its history, so you have a previous decision, then you can maybe kind of trace it back. But even there, it gets hard.
But I mean, we see plenty of examples where the pattern generated shows up like nowhere in the training data.
Yeah.
Yeah, on the other hand, I'm aware of some research that tries to analyze if there's any kind of data leaking that's happened for MT models. For example, if your model generates this output, then by some possibility, it's looking at this data set, which might be like confidential or whatever. It's more on the line of like a privacy research. So first thing, I don't think that relates, how much that relates to the question that you were talking about. And secondly, I don't think they use anything that's related to interpretability here. Yep. But
I mean, in the line of work of privacy, I mean, has anyone tried to measure how much of the training corpus can be just replicated? Like, I mean, if you retranslate the training corpus, how how accurately?
Right. I think that's roughly what that paper I'm talking about is doing.
Thank you. Thank you so much.
Thanks.